In this section, we're going to look at some methods for evaluating limits analytically. We're going to start with a definition. So we saw last section that it's possible for the limit as x approaches c to be equal to a value that's not equal to the function value. But when it is equal to the function value, we say that the function f is continuous at c. All right, so here are some basic limits that you should know and be able to use freely. So the first says that the limit as x approaches c of a constant function, the constant function b, is b. So remember, this is just the graph of this function just looks like a horizontal line at y equals b. And so surely as you approach some value, any value c, the limit here is going to be b. All right. The limit as x approaches c of the function f of x equals x is c. Again, just quickly think about the graph. Here's f of x equals x. And remember, all the points here look like c comma c. And so as you approach c from the right or the left, and the left, the y values also approach c. And finally, the limit of x to the n as x approaches c is just c to the n. All right, so now that you have these, you can use these freely without plugging in values anymore. And so let's see how to do that in just a second. I want to give you some more properties of limits. So let's suppose that f and g are functions who have limits as x approaches c. So the limit of f of x here is going to be L as x approaches c, and the limit of g of x as x approaches c is k. Then, first of all, if I multiply f by a constant, I could just pull that constant out front, is all this is saying. So the limit of b times f of x is the same as b times L. If I add or subtract f and g and take the limit, then I just get L plus or minus k. If I multiply f with g and take the limit, then I'll just get L times k. If I take f over g and take the limit as x approaches c, I'll get L over k, provided that k is not 0. And finally, if I raise f to the power n and take the limit, then that's the same as just L to the n. All right, so you want to have these properties handy in front of you as we do some examples. Let's start with the limit as x approaches 2 of f of x squared minus 7. Okay, so by the properties of limits, by the second property, I know that this is the same as the limit as x approaches 2 of 5x squared minus the limit as x approaches 2 of 7. That was property 2. Property 1 on the last slide says that I'm allowed to pull this constant 5 out front. So this is the same as 5 times the limit as x approaches 2 of x squared minus the limit as x approaches 2 of 7. And now these two limits are basic limits from the first slide. Okay. So I have 5 times, I'm allowed to just plug 2 in here, times 2 squared, minus the limit as x approaches 2 of 7 is just 7. Finally, this is 20 minus 7, which is 13. All right, here's another fact that's going to be useful. If p is a polynomial function and c is a real number, so like our last example, 5x squared minus 7, that's a polynomial, then the limit as x approaches c of the polynomial is just p of c. Also, if we have a rational function, so remember a rational function just looks like a polynomial divided by a polynomial. And we know that q of c, the denominator, when I plug in c, is not 0. Then the limit as x approaches c of that rational function is also just r evaluated at c. Okay, and that just comes from those properties of limits, just like we saw here. If I plugged in 2 directly, whoops, I got 13. Okay, so let's find the limit as x approaches -1 of this rational function. Well, I need to check that if I plug in -1 to the denominator, I won't get 0, and I won't. So by this theorem, I'm allowed to just plug in -1. So I get 2 times -1 cubed plus 3 times -1 minus 8 divided by -1 plus 2. And what is that? I have -2 minus 3, that's -5, minus 8 is -13 divided by 1, so -13. All right, here are 2 more useful theorems. We're going to see a lot of theorems in this section that will make it easier for us to compute some limits analytically. So this next theorem says that if I take the limit of the nth root of x, and as I approach c, then it's equal to the nth root of c. So I'm allowed to just plug c in. That's true for all c when n is odd, and it's true for positive c when n is even. Remember, we can't plug in negative values into an even root. This next theorem tells me that if I compose functions, if I want to take the limit of the composition of functions, I can take the limit inside. So if I know that the limit as x approaches c of g of x is L, and the limit as x approaches L of f of x is f of L, then the limit of f composed with g of x as x approaches c, I can pull the limit inside. So it's f of the limit as x approaches c of g of x. And now this limit is just L. So that's equal to f of L. Okay, so let's try applying those theorems. So the first one, I want the limit as x approaches 3 of the square root of x squared minus 1. Now inside of that is the function x squared minus 1, which is a polynomial. So we know from the previous couple slides that the limit as x approaches 3 of a polynomial, x squared minus 1, is just what I get when I plug in 3. So 3 squared minus 1, which is 8. All right, so that limit exists. And we also know that the limit as x approaches 8 of the square root of x is the square root of 8. So by the last theorem on the previous slide, the one that says if we have the composition of two functions, we can bring that limit in, we can conclude here that the limit as x approaches 3 of the square root of x squared minus 1 is the square root, let's write it this way, the square root of the limit as x approaches 3 of x squared minus 1, which is the square root of 8. All right, similarly, the limit as x approaches 3 of the cubed root here of 2x squared minus 18 is equal to the cubed root of the limit as x approaches 3 of 2x squared minus 18. Now that limit inside is 2 times 3 squared minus 18. 2 times 3 squared is 18, and so when I subtract 18, I get 0, so this is the cubed root of 0, which is just 0. All right, trig functions. All of the trig functions are continuous on their domains. Okay, so if c is a real number in the domain, the limit as x approaches c of any of the 6 trig functions can be found by just plugging c in. Okay, so that's what this theorem is telling us. And let's try applying that here. Okay, so in example 1, I want the limit as x approaches 0 of cosine of x. Well, 0 is in the domain of cosine, so this is just cosine of 0, which is 1. What about the limit as x approaches pi fourths of x times sine x? Well, remember from our properties of limits, if we have a product of functions for which the limit exists, then the limit is just the product of their limits. Okay. So I'm allowed to just multiply the limit as x approaches pi fourths of x times the limit as x approaches pi fourths of sine x. And for both of these, I'm allowed to just plug in. So this is pi fourths times sine of pi fourths, which is pi fourths times the square root of 2 over 2, which is pi square root of 2 divided by 8. Sine squared is just sine times sine. So this again lets us use the property that we're allowed to multiply by the individual limits. So this is just going to be the sine squared of pi, which is sine of pi squared, which is 0 squared, which is 0. All right, here's another theorem. Suppose we have a real number, c, and let f of x be equal to g of x for all x not equal to c in some open interval containing c. If the limit as x approaches c exists, then the limit of g of x exists, then the limit of f of x as x approaches c exists, and they're equal. Okay, so remember in the first video, I asked you to graph this function here. And what we found was that x cubed minus 2x squared plus 3x minus 6 divided by x minus 2 factored on top as x minus 2 over x squared plus 3 over x minus 2. And so you can cancel the x minus 2's and get x squared plus 3. So this function is equal to x squared plus 3 everywhere but x equals 2. By the theorem, then, this limit is going to be the same as the limit as x approaches 2 of x squared plus 3. And this is a polynomial, and so we're allowed to just plug 2 in. So this limit here, I've run out of room, let me come up here. This limit is just 2 squared plus 3, which is 7. Now, if you remember when we graphed this function, we said it had a hole there at 2, but it looked, as we approached from the right and the left, that it was approaching 7. Let me just show you the graphs real quick. Let's see. We had x cubed minus 2x squared plus 3x minus 6 all over x minus 2. And we're zoomed in here from our last graph, so let me pull out a little bit, and there you can see it. Now it's hard to see the hole when we're so zoomed in. There should be a hole here when x is 2. There, that went past. 2 undefined. All right. But as you approach 2, you can see that it's approaching 7. All right, so here's some strategies for finding limits. First, learn to recognize which limits can be evaluated by direct substitution. We just gave you a big chunk of functions for whom the limits can be evaluated by substitution. Okay, so take that to your advantage. When the limit cannot be evaluated by direct substitution, try to find a function that agrees with f for all x not equal to c. So just like that last example, we were able to cancel, and so that function agreed with a polynomial whose limit we knew how to find. And finally, use a graph or a table to reinforce your conclusion. So go ahead and graph the function and zoom in to what you're looking for, and make sure that it agrees with your conclusion.